this guy right here, it's going to be negative 3/5 v naught. It's a 3 there. Uh-oh, I just made it worse. Try again. Right. So I just go back. It's this component. It's this component right here. That component of that initial velocity. So that's 3/5. Uh-oh, I picked up a ruler. And then ABY, that's gravity, which in this case is negative 32.2 feet per second. Right, when we deal with feet, that's 32.2. Right, because everything else is in feet, so we'll keep it in feet. Right, so then this equation just becomes 100 minus 3/5 v naught t minus 1/2 times 32.2 t squared. Okay. At that point, we're done with the hard part. Okay. At this point, we have essentially we have 4 equations right here. 2 of them are equal. So we end up with 2 equations and 2 unknowns. The 2 unknowns that we have to solve for are going to be v naught and time, right? Those are the only 2 variables you see in all these things, right? So what we do at this point, we set the x positions equal to each other. Right? These guys get set equal to each other, and these guys get set equal to each other. Okay? How did I do that? I put it in my calculator. My calculator will do 2 equations and 2 unknowns. So I just plug them in. Boop, 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 boop. It takes about 2 seconds. It goes calculating, and then out pops the solution. Right? You can also do it by substitution. Right? You can solve for one of the variables and substitute it back in. There's all sorts of ways of doing it. I think the easiest way is use your calculator. You can use it. I'm telling you to use it. Please use it. Use it. Okay? I'm sure, I believe the TI 80s, 83s, and 84s will do it as well. TI 89s will do it better. The Inspires will do it even better, okay? You could use them now. It's almost cheating. It's like a cheat code. Do it. All right, any questions about that one? Right, just come up with those equations. So there's another one, another group of problems I keep talking about. We'll go through this pretty quick, right? All of the problems we've done so far have been, I give you an acceleration, then you get velocity, and then position, right? And it's going that direction, acceleration, velocity, position. This is one where I'm gonna give you the position, and then we're gonna say stuff about the acceleration. So it's going the opposite direction, which is easier. I think you have at least one homework problem related to this. Okay, so this is just a simple projectile motion problem, right? And something some projectiles being launched, and it's going to go, down a certain distance, and we're going to be messing around with that thing. So we're given the x position is a function of time, right? There's no acceleration term, it's just a velocity term. And then the y is a function of time, which you should recognize that 4.91 is 9.8, I guess that's 9.82 feet per second. So that's the acceleration due to gravity term that's over on the right there. Anyways, regardless, that's what we're given, is the x position and the y position. Right? And so what we're then asked to do is tell me what the acceleration vector is, the velocity vector is, the height h that it reaches, and the range L, okay? So the way I did this problem, right, is I just came over here and I wrote down x as a function of time that was given to us. That's 86t, right? My velocity is just going to be the time derivative of it, so it's just x dot is equal to 86, and again, that is the velocity in the x direction. So I just take the derivative of 86t, right? And then the acceleration is going to be the second derivative of that. So the derivative of a constant is just 0, and that's ax. That's not the vector. That's not acceleration vector, but that is, right? But it is the velocity and acceleration in the x direction of that particle. Do the same thing in the y direction. Y is a function of time is equal to 96 minus 4.91 d squared. Y dot, the velocity in that direction, just going to be 96 minus 9.82 t. And so we picked up a little off of gravity right there. That's going to be equal to Vy. And then y double dot, derivative of this. 96 go away. Oh, I did something wrong. There's a t, missing t right here. I wasn't done yet. I was going to say what was wrong. I just was going to say that. I was going to say what's wrong. That was wrong. This guy left the t out. Perfect. Good job. Good job finding that, guys. All right, take the second derivative now. Just drop that t. 9.82 t. That's the acceleration in the y direction. And see, these ones are easier going this way. Huh? I wasn't done yet. I was just gonna say, what's wrong here? There's a negative there. Good job. See, isn't that a great technique? You guys never know that I'm making mistakes. So, I just want to be truthful. A couple of those were actual mistakes. Didn't know if you knew that. Okay. All right. So that's actually not what it asked, right? Those, now I know the acceleration. Now we just have to put it in vector form, okay? So the first one was, what is the acceleration vector, right? So what is A? So that's just going to be AX in the I direction plus AY in the J direction, right? So in this case, that just becomes negative 9.82 in the J direction. And watch this. I'm going to put units. What is the units on this one? Oh, it's meters per second squared. Now again, I'm really loose with my units, as in I don't use them until the very end and I put them in. Okay, but just do you, right? If you can get away with that, then do it that way. If you can't, start using your units all over the place. It's probably better, especially when you're learning, to not be all willy-nilly with it. Okay. So that's my acceleration vector. Second part of the problem says the velocity vector at t equals 0. Let's write the velocity vector first. Velocity vector, it's just going to be Vx in the I direction plus Vy in the J direction. That's 86 in the I plus 96 minus 9.82 t, and all of that in the J direction. And so I kind of put it in parentheses just to say that both of those in the J direction. So that isn't at t equals 0. That's just our velocity vector. And to get it at t equals 0, you just put in t equals 0 into that above equation, and we get 86 in the I plus 96 in the J. So that's the initial velocity of that projectile. Okay. Part three said, what is the max height that it reaches? How would you do that one? Let's see here. Nate Dog, what would we do? Oh no, I learned another one. Mark, what would we do? I learned a new one yesterday. I did. What's the max height? How would I find the max height here? Yeah. You're thinking about maximization stuff, but think about it. It's coming up, right? This projectile, it's coming up, and then it's going to start coming down. What's the velocity going to be like right in the y direction? Yeah, there you go. So the velocity in the y direction is going to be 0 when it hits the max, right? Because it's going like this, got a velocity this way, and then it's 0, and then the velocity's down that direction. So it is the derivative. It's the derivative of the position you set equal to 0. So if you're thinking in terms of calculus and you're maximizing and minimizing, you set the derivative equal to 0. If you're thinking in terms of physics, right, it's velocity up, and then its velocity comes back down, right? And so we're going to do that. Okay, so then we're going to set the velocity in the y direction equal to 0. right? Max height when Vy is equal to 0. 96 minus 9.82t equal to 0. Plug that bitch in my calculator. You didn't, right? T is equal to 9.78 seconds. Okay, so that's not my answer, right? That's how much time it took, right? So we found the time it took to reach the max height. Now, how do I get the max height? Plug it back to that into my y position, right? My y position. Plug that back into my y position. So y of t equals 9.78. If I plug it back in there, I get 469 meters. Yeah, see, this is easy stuff. You got this. Okay. Fourth one, it asks for the range L. Ooh, what are your thoughts on the range L? It is, yeah, you're going to use the x position at some point, but what do I use for the L? I mean, for the time.
You're going to calculate how long it takes to get down to the 120 meters.
Yeah, that. Yeah. That would be what you said is the case if it was the same height, right? But it's going down further. So it's not going to be, it's not halfway. Right? It would be halfway if it hit the regard, but it's not. So then we have to find the amount of time that it takes for the y position to go to negative 120. And then that'll tell us how much time. Then I take that time and I put it back into my y position, or x position rather. Okay? All right, so let's do that. Y is equal to 96t minus 4.91 t squared. Right? That's my position in the y direction, right? And I'm going to set that equal to negative 120, right? Because it's going to go up, then it's going to come back down. So we can figure out how long it takes to reach negative 120. Plug that in my calculator. I get t equal to 20.73 seconds. Right? So then I come back to x position of t is equal to 20.73. Plug that in. I get 1783 meters. A similar problem, I think, in your homework with a golf ball. Is that anybody? No. We do their homework. It's due tonight. Oh no, it's not. I said you could turn it on Monday, right? I set the due date on Monday. So, and I know you're like, well, we don't have class Monday. I don't care. Grade scope, you could turn it in, whatever, okay? And so it's actually technically due today, but I'm giving you till Monday to do it. So that'd be a good activity for Labor Day weekend, right? No class on Monday, by the way, right? So hopefully you're aware of that. Labor Day weekend. Okay. Any questions about that? I like this way. This is easy. Going this direction is easier. This is more high school physics stuff right there. Okay. So let's go into a new realm, right? Think of angular motion. All right, we have to define some angular motion first, then we use this quite a bit. Actually, throughout the whole semester, we're going to use this angular momentum or angular motion. Okay, so this thing starts out. So this is if we have things that are rotating. We're gonna have lots of stuff that's rotating in this class. So what we're gonna do is we start out our particle. We'll just say the particle is a point that's traveling along a path. But instead of measuring it like velocity, acceleration, Cartesian coordinates, we're gonna track it based on its angle it is relative to the angle it used to be. So we're gonna define this thing as being theta down here, and then that thing's gonna move slightly, right? And so then it's going to have a new theta, right? It's going to change, right? That theta went from being that size to a theta being bigger, okay? So that increased in size. That when it changes when a change in theta, we're going to call omega. We're going to use this heavily throughout the semester. So omega is our angular velocity. It's how is that angle theta changing with respect to time. And sometimes we're going to use this pretty interchangeably. We call that theta dot as well, right? It's a time derivative of theta. How is theta changing with respect to time? And what's theta? Theta is just that angle that we're pointing to that position, okay? That's called omega, right? I think you've done a little bit of this before, right? And then alpha is how, that is our angular acceleration, and that's how our velocity, angular velocity is changing with time. It's the second derivative of omega with respect, or sorry, second derivative of theta. Second derivative of theta dt. Right? It's more shorthand here. This would be theta double dot, or you can also think of it as omega dot. All just different ways of writing the same thing. Alpha is angular acceleration. Omega is angular velocity. Right. I don't even do. I'll put some units. Let me just do some units. It looks like I've done this class a bunch of times. That's radians per second. Radians per second squared. All right, I'm gonna give you a little, I think in your next week's homework, there's a problem 13.100. This is just a little help. They give you alpha in this problem. They give you alpha as a function of theta, which is the same as acceleration a function of position, right? Theta is the position. So the stuff we learned before about acceleration being a function of position and how you go about solving those problems apply here too. Even though it's slightly different, right? Instead of having a function of s, right? Now it's a function of, or alpha as a function of theta. So this is just some foreshadowing. And so what we did before is we used the chain rule, dt, that's equal to d omega, d theta, dt, and this is just omega, right? That's a little hint. Right? And at that point, you'll put all the omegas on one side and the t's on the other side, and then you'll solve it that way. That's just don't miss it. It's the same thing, right? It's an acceleration of function of position. Instead of a function of s, it's alpha function of theta. Okay, back to this. I just don't want to forget that. So we've defined those things. Okay. We can write these things in terms of vectors as well. Oh, vector notation. Right? So my omega, this is going to come in really handy to do it in vectors, is going to be omega in the k direction. This one always blows my mind a little bit. When you start talking about things that are rotating, right? What you do is take your hand, the right hand rule, right? Take your hand and you rotate your fingers in the direction that the thing is rotating. So if I'm going to, in this case, the way I have it drawn, I put, right, my omega, right, that vector right there that's pointing up like this, it's rotating this direction, right? Because it's going from the black to the red. So it's rotating like that. So what you do is take your hand, you rotate your fingers in the direction of that omega, and the direction that your thumb is pointing is the direction that that rotation is going, right? So it's in the k direction. Or you can think of which axes is the rotation taking place about. So in this case, that omega is taking place about the k direction, right? And so then if I would have drawn it the other direction, right? If I would have drawn it going this way, right, omega, so that angle is getting smaller, then you do the same thing. I would take my fingers and I would rotate it this direction, and now my thumb is pointed towards the board, which means it's a negative, right? So that's just our sign convention we're gonna use. If your thumb's coming out of the board, that's a positive omega. If it's going into the board, that's a negative omega, okay? Same thing applies with alpha as well, right? So if I draw it like this, if I draw alpha, right? If the angular, if that omega is changing, positive, you rotate this direction, my thumb is going that way. So that my vector here would be alpha, would be equal to negative alpha in the k direction, right? And this is just as shown. Right? The way that I drew it up above, that's true. Okay? And understand that right-hand rule, we're gonna use it a lot throughout this whole semester. right? Always, it's really funny at the end, like when we do, well, because then, so this is, right now we're just doing planar, X, Y, our rotation, when it's fixed on that plane, right, all of our omegas and alphas are gonna be in the K direction, but if you're doing 3D motion, that's not the case. If 3D motion, you could get rotation about, this axis, and then you could do it about this axis, right? You could do it about all 3 different axes. And so your omega and your alpha can actually have the X, Y, and Z direction. And so when we're doing 3D stuff at the very end, the final is just everybody sitting around doing right-hand rules as they go along, right? And then I used to make a joke, be like, you poor left-handers trying to do the right-hand rule, right? I mean, that's like, and then one of the lefties spoke up and said, actually, it's easier for us because while we're doing the right-hand rule, we could be writing. So use that to your advantage, right? So you could be doing the right-hand rule, and then you could be moving along as you're going. Any lefties in here? There you go, Mark. There you go. You have an advantage. You got one too? Yeah. You might look a little uncoordinated trying to do the right-hand rule, but okay. Okay. So that's that. We defined that. We're going to use that quite a bit. So then sometimes we're going to need this for the derivation on the next page, right? So a base vector could change. So if we start out with a base vector and call that E hat as a function of time, and then it's going to change to another one, E hat of t plus delta t. A short time later it changes. And then there's going to be a vector that points up to that. We'll call that delta E hat. Right? And this would be assuming that there's a positive omega. Right? Omega is how that's changing with respect to time. So it's going from E to E plus delta T, a change in time. And there's this little vector between that points in, we call that delta E. Right? And then the book spends a bunch of time kind of proving this, but we're going to jump right to the case. We'll say that delta E is going to be perpendicular to E. Okay? It's basically saying that this is going to be a right angle right here. It's not, in a differential sense it is, right? Right? If you imagine the red and the black coming together, then it would be that way. I mean, red and black are the same length, and so really, like from this perspective, it isn't going to be perpendicular because it's got to go point back. It's going to be a little bit short. It's going to point back this way. But a differential sense, as that thing approaches the same, it is going to be perpendicular. Okay, so delta E is going to be perpendicular to that, and so we're going to define this new thing, a new vector called n. That's going to be perpendicular to E. The n direction is perpendicular to E. Okay. And then what it says is this. So this, like I said, we're going to use this. We're going to use this in the derivations. We're kind of going to jump a little bit, but it's all based off of that what I just said there. If you could trust me that change in position is going to be normal. Normal meaning perpendicular. That's what the n there is for. If it's normal to the original vector, then we're good. Okay, and so that's where they get this next little thing they say. The time derivative of how E changes with respect to time is going to be how theta changes with respect to time, perpendicular to what E originally was. That's what this says right here. Right? The derivative of this base vector changing is just going to be d theta dt, which is omega, times the n direction. Right? So it's omega times that in that direction. Okay. Again, the book goes through a big derivation. If you want to look at it, go ahead and do it. Okay? If not, just trust me that this is gonna stand true. Okay. So in the n direction. So then this too could be written in vector notation. Again, important to understand this little thing. You'll understand the next page when we do a derivation, and this is going to pop up, and it'll be good to have that component. But you can also do this in vector notation too. If you take, we're going to define this as dE dt. So how is my base vector changing with respect to time? That's going to be omega crossed with E. You guys remember cross products? right? So it's going to be the cross product, because now we're doing it in vector notation, so it's a cross product. And so the way you do this cross product, okay, is so just for our, that's all. We're not going to dive too deep into cross products here, but the way you do a cross product, if you wanted to know which direction it's going afterwards, is you take your fingers and you point your fingers in the direction that this is pointed, and then you curl your fingers, then you curl your fingers in the direction that this is pointed, and then wherever your thumb is pointing is the direction that that cross product is going to take place. And you're like, what the hell are you talking about? So let's go up here. Let's do, in this case, we're doing omega crossed with E. So my omega, just find which way my omega is going. I roll my fingers in the direction of omega, which is like this, right? And so my thumb is pointed out. So omega is pointed out, okay? So to do this cross product down here, I take my fingers and I point them in the direction of omega, and then I curl them in the direction of E, and E is pointed up to the right there. So would you look at that? My thumb is pointed perpendicular to that. Look how cool that is, huh? It's not that cool, but maybe don't bring that out at a party tonight. But this is the slinky, absolutely. This maybe not, okay? Fingers out in the direction of omega, curl them in the direction of E. My thumb is pointed perpendicular to it. Right? That right hand rule thing is going to come in super handy throughout the semester. Any questions about this? I know it's like, what the hell are we doing this for? So let's show you what we're doing it for. All right, everybody cool? Omega is changing theta as respect to time. Alpha is changing omega with respect to time. Right? One's a velocity, one's an acceleration. Right? And then we're going to use the space vector changing thing in a derivation on the next page. All right. All right. So we just did Cartesian coordinates. You treat these things different. Now we're going to do a normal tangent coordinate system. Sometimes it's easier to use a different coordinate system, right? And you're going to be like, oh my God, that doesn't make... We'll show you some examples, especially polar and cylindrical coordinates are super helpful with certain types of problems. If you have anything that's ever like spinning and stuff, it's important to use these different coordinate systems. And so we're going to do one of these ones, okay? You use this when the path is defined. Sometimes you'll get an equation that says this is the path. Okay, this is what x of t is what y of t is. This is I'm going to define the path. If you have something like that, it's going to play out. It's going to be helpful. Okay, or if there's something rotating. A lot of times the normal tangent and polar coordinates kind of like end up on top of each other, especially when we're dealing with circles. But we'll get into that later. But something's rotating is another place that you would use these things. Okay, so the coordinate system in this case are normal and tangent to the path, as the name implies. So if I'm down here, okay, I would have at this particle at this location, right? Say it's moving to the. We'll say that it's moving to the right. Right. So tangent to the path, I'm going to have. Right. At that instant, it's tangent to the path. That's one of my coordinates, and the other one is normal to the path. It's going to point back like this, okay? We'll call this ET hat, and we'll call this EN hat. Okay? And then that's pointed back to a point right here. Okay? And what do I define that? Okay. Okay, so let's define some of these variables. ET hat. Okay, this is a unit vector. Unit vector, tangent to the path. Okay. That's what EN hat is. Or sorry, ET hat is. EN hat is equal to a unit vector, normal to path. A little bit you need to see, obviously that would be the case, but then we're going to add a little bit more to it. This is pointed in direction of instantaneous center of curvature. Unit vector, normal to the path, pointed in the direction of instantaneous center of curvature. Okay, we just find a couple terms. We'll come back and show what's going to happen with these. This is going to be another variable I want to label is S. That's the distance along the path. I don't know why I didn't type that one, but I didn't. And rho is the radius of curvature. Okay. So what's interesting about this coordinate system that we haven't dealt with before is that our coordinates are going to be changing, right? So right in this case right here, if I have it drawn, right, it's like this, right? They're perpendicular to each other. But as I move along that path, right, it's going to be changing, right? It's going to go up a little bit. It's going to go like this. And then the normal has to point back to the center of curvature. So up at the top there, you'll see that the center of curvature is actually down. So my coordinate system is going like that. And then it's going to go like that along the way, right? Which is new to us, right? Before, when you do Cartesian coordinates were sitting over here, right? They're sitting over here and they're not changing. They're just sitting there and nothing's happening to them. But now my coordinate system, it's going this, it's going this, it's going this, it's going this. And then over here, it's going this, and it's going this, right? And so it's moving, it's changing as we move along that path, right? And so let me draw it over here just so you can see, just solidify that point. Right. This ET and then my EN hat is going back that way. Okay. So those coordinates are changed. This is not pointed in the same direction as it is here. It's slightly off, and this is obviously going that way, and that's going this way, right? Rho that is talking about the center of curvature. This is pointed back. Right? It's pointed back this direction. That distance there, that's the rho. Right? It's going around a curve, and that rho can be changing as a function of time too, because there's nothing. Right? It is. I mean, because at some point rho is going that way, and the other times the rho is pointing the other direction. And then s would be just the distance along that path. Okay. So what we're going to do on Wednesday is we're going to define velocity. Okay. In this coordinate system, okay? But also, I just want to point out, this is why we just did that. You know, earlier, if you look back a couple of pages in our notes, we got to a point where we took the derivative of our coordinate system. When it was Cartesian, we took the derivative of our coordinate system. It just went away, right? It was equal to 0 because our coordinate system didn't change. Now when we get to the point where we take the derivative of the coordinate system, now our coordinate system is changing, so then I need to account for the fact that my coordinate system is changing, hence what we just did, because we're going to take this is taking the derivative of a coordinate system, right? So this is what we did previously. So that's where we're headed, okay? And then we'll do a couple, we'll finish this up, we'll do a couple of example problems, and then move on. So I will assign another homework today, just kind of keep the ball rolling. So I'll see you guys on Wednesday, and have a good weekend.